All right, this is lecture number 3 in this topic of minerals and mineralogy. If you're into this, and my YouTube channel has a whole class based on mineralogy and another whole class based on gems and gem minerals. So there's more here available if after these 3 you feel like you haven't gotten enough. In our textbook, this is chapter 3 as well. And what we're going to do today is I want to talk about families. Some major groupings of minerals that share composition and structure with one another. And I'm just gonna boom, 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 go through these and we'll see how long this takes. The most important family of minerals, I contend, is the silicate family. These are known as the rock-forming minerals. Because whether you are sedimentary, igneous, or metamorphic, the odds are very good that most of that rock is going to be comprised of one of the silicate minerals. A silicate is defined as something with an SiO4 unit. And so what an SiO4 means is that there's a silica bonded in a tetrahedral arrangement to oxygens. I'll do oxygens here as these open circles. All right, so this is O2 minus, and there's 4 of them, and there's a silicon 4 plus in the center of that tetrahedron. In fact, let's go ahead and say that SiO4, and this unit would have a net charge. It's 1 4 plus, it's 4 minus, there's a 4 minus, and this is called a silica tetrahedra. All right, so that is the building block for the rock forming minerals. These rocks make up the majority of the upper mantle. 90% of the crust is actually made of silicates. This is quartz, this is feldspar. You've heard of these before. Now, silicates themselves have subfamilies. And so I'm going to redraw this silica tetrahedra, but in a simpler way. I'm going to draw it as a triangle. And what you picture is, here's an oxygen, here's an oxygen, here's an oxygen, and here's an oxygen. And somewhere in the middle of that triangle, there is the silicon. And the way that the subfamilies are divided within the silicate family is if the silica tetrahedra sit by themselves, or if they bond with one another to form chains. And so these 2 features that I've drawn here are 2 of the different subfamilies of the silicates, based on how this one has a bridging oxygen that bridges 2 tetrahedra together. Some silicates have a whole framework of these things built all structured together. All right, so let's go through the various important silicates, and the first I'm going to teach you about is the mineral quartz, or at least introduce you to today. So here's quartz. Let's go with a picture of quartz. There's a great picture of quartz. A single crystal, high, beautiful transparency, and chemical formula for quartz is SiO2. There's a lot of things you could learn about quartz. The most important is probably that it's going to sit with a hexagonal structure. So you should expect to count 1, 2, 3, 4, 5, 6 sides as you go around the pyramid at the top, or this prism that makes up the body. And when it breaks, it actually has a conchoidal fracture, and it has a density, or a specific gravity, I should say, of 2.7, which is normal. So we count them up, 1, 2, 3, and on the back there'll be 4, 5, 6 sides. Look at this right here. That is an example. I covered it now, but you can see here some conchoidal fracture where one of those crystal faces chipped off. Quartz occurs in all rocks. No, that's not true. Not all rocks, but many rocks. Granites, sandstones in particular. These are going to be environments that are comprised significantly of quartz. So in this example over here, which is the granite, it's all this gray material in here. This is all quartz. Using a vocab word you've learned before, it's anhedral. The sandstone in this picture from Arizona, every grain of sand, if we were to zoom in and look at this in our hands or even in a microscope, almost every grain in this picture is going to be a grain of sand that has survived the weathering and erosion process and then deposited with these beautiful crossbeds. All right, so quartz is an important member of the silicate family. The next mineral that I would like you to know within this family is called feldspar. Now, in a later class, you're going to learn that feldspar is itself a group of different minerals that have this formula. They're Na, so they're sodium, potassium, aluminum, silicon, and oxygen bonded. And depending on the ratio of these to one another, they're going to have different names, but it's this family that makes a huge part of the lower crust. So in terms of what rocks do feldspars form in? Well, it's one of these things where it's like a lot of rocks have feldspars in them. They tend to be white to gray to pink. These are going to be the basic colors that you're going to see. So in any granite, actually in this granite we've got a lot of pink, right? And so this is a potassium feldspar. Up in this picture, which I showed before, the pink is also potassium feldspar, but the white, that's a sodium feldspar. So this granite up top actually has two different types of feldspar in it. Now this other rock that we have over here, this is more an igneous volcanic rock. All these big white crystals are feldspars, maybe with calcium. I forgot to put calcium. Oh, professor would have been mad at me for forgetting calcium. Calcium, sodium, potassium, aluminum, silicon, or oxygen. A lot of different things, but those are the cations that matter for the feldspars. Do I need to say, I should say something like granites, lavas, sandstones. A word, we're going to say gabbro. You don't know gabbro, but you'll learn gabbro soon. Anyway, that's what like the lower crust is. Oh boy, there's so many feldspars in the crust. All right, and now the third type of silicate that I want you to know is called olivine. And the rhyme about olivine is that olivine is olive green. And it is, how about for this class? Let's just say it's greenish and get away from the cuteness of that rhyme. But I'm going to show you two pictures that emphasize green. And the first is this picture. This is a basaltic lava that brought chunks of the mantle up to the Earth's surface. And what this tells us, okay, so this right here is olivine, and they're all anhedral. So they tend to be anhedral. Why am I writing? All right, they tend to be anhedral. And the key here is that it's the upper mantle. Upper mantle is composed, 90% of the upper mantle is composed of this greenish mineral, this olivine. And so in this picture of the layers of the Earth going from the crust to the upper mantle to the middle mantle, down to the lower mantle, down to the outer core and the inner core, notice how this is green here. The artist has done well to represent olivine. The chemical formula for olivine is Mg2SiO4. So it's a magnesium bonded to that silica tetrahedron. All right, there's our first family that I wanted you to know. The next family for learning are the carbonates. All right, so what is this family? So this is going to be the carbonate group, the carbonate species, carbonate. And the carbonate basic unit is CO3 2-. And that CO3 2- bonds with some like metal cation and maintains charge balance. So MnCO3 is 1, and MgCO3, that's another. These are examples of carbonates, but the most famous of all the carbonates is calcite, and calcite is calcium carbonate, CaCO3. I've mentioned it a number of times over the course of this semester. This is what limestones are made of when we have shells and corals. Biocorals biomineralize from seawater that calcium into their body parts, then those will die, and that is what will make a limestone. And if a limestone gets metamorphosed, this makes a rock type called a marble, which I'm sure you've heard about. This is the significance of calcite. What are the other things we've talked about with calcite? It fizzes with hydrochloric acid. Oh yeah, and I taught you about how it breaks into these rhombs because it has a perfect rhombohedral cleavage. Yeah, calcite's a magnificent mineral. Here we go. Let's put in a picture of calcite. Oh, let's put it here. We can start with the individual picture here on this side. Here we get this nice rhomb shape. You can even see a cleavage starting to form right here. See that? There's a cleavage actually forming inside of this, so this could be breaking fairly soon. And then a picture on the side, this is a marble quarry in Italy, just showing how you can have these really rich deposits of calcite that are used for economic purposes, building, sculpting, etc. All right, our next family to get into are the oxides. Oxides are important because these are the great ores for metals. The oxides. An oxide is oxygen 2- plus some cation bonded together. And so we could have something like Fe3O4. That's a mineral magnetite. Notice how it's a cation bonded to an oxygen, and there's charge balance. Another example could be TiO2. All right, that's an oxide. And so these end up making the metal ores that are so important for our economy. The metal ore mineral that I want you to know for this class, which is intro, in later classes you can learn a lot more than this, it's hematite. And hematite is this reddish brown hematite, Fe2O3. And it tends to be red brown. And it is our primary ore of iron. If you were to pick up a single chunk of hematite, it's going to look like this red to reddish brown color, but there can be whole mountainsides made of this material. So it lends itself to wide-scale mining activity, which is great because we need steel and iron for it. Now, it can also occur in many, many other situations. In fact, I would like you just to kind of like say, anytime we have iron, so oxidized iron in many environments. That is how we get hematite. And it could be just in between grains of sand, giving us a brownish red sandstone. It could be the whole planet of Mars. Basically, hematite is abundant in many different environments, and it can stain those things the reddish brown color. Now, to finish, kind of just for fun, I wanted to just speak a little bit about gemstones, because this is one of my passions. And when else do you get to learn about gemstones? A couple key criteria for gemstones is that they need to be hard, they need to be rare, and they need to have good optics. This is going to be your combination for if a material is a gemstone, because hard lends itself to wearability and durability. Rare lends itself to value, and optics to beauty. And in some minerals, these things all combine together, and that makes it valuable to us, whether it's an emerald, a sapphire, a tourmaline, or a garnet. But most of us will buy or give a diamond in our lifetime. So what I wanted to do was take an opportunity to discuss diamonds as minerals. And here within my notes, I just have a couple main points. So diamond, it is carbon. And the carbon in diamond is bonded in a tetrahedral arrangement, like that SiO4 was. But here it's 1, 2, 3, 4. Let's see, boom, 5. It's 5 carbons stacked together in a tetrahedral arrangement. And we could even say that. We could say tetrahedral shape. And we'll say tetrahedral arrangement of carbon. And it's covalently bonded. And those covalent bonds are incredibly strong, which is what takes us to it having a Mohs hardness of 10. And Mohs hardness of 10 means this is one of our strongest and hardest. It is the strongest and hardest minerals. Now, diamond is also beautiful because of its stunning optics. And so over here on this side, let's go excellent optics. And it's not just one optical criteria that can make it be such a beautiful and coveted faceted gemstone. It's actually multiple things. The luster of diamond is adamantine. That's the descriptor we use for diamond. And what adamantine luster means, it actually reflects 20% more reflectance than you would expect. And that gives an incredible sparkle. In fact, I'm going to say more than 20% reflectance than that what you could expect. Another excellent aspect of the optics is that it has a very high dispersion. High dispersion, associate this with the word prism. You know how prisms make rainbows? That's what high dispersion does, and that's why when white light enters a diamond, it can actually break it up and make different colors of the rainbow show up. Another aspect of the optics that I would like to get into right here is color. Now, most color of diamonds is, we would say, colorless. And when you have a colorless diamond, the lattice of diamond is just carbon, 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 carbon. But yellow diamond is actually fairly common, or at least pale yellows are. And to get a pale yellow diamond, you actually just replace one of those carbons in the lattice at something like, let's say, like 1,000 ppm concentration level of nitrogen. So if you replace a carbon with a nitrogen at around 1,000 ppm, very low trace amounts, you can actually make a yellow color. And if you do that with if you do that with boron, you can actually make a blue color. This is what the Hope diamond is, but it's even at like the parts per billion level. Very small amounts can change the color of a diamond. Now, let's talk about the mantle and the diamond, and then we'll be done here. Diamond is the stable form of carbon deep inside the earth. So if we drew an axis of temperature versus depth, there is a stability field where everything at shallower depths than this line, graphite is the stable form of carbon, and below that line at great depths, diamond is the stable form of carbon. Now, as we go deeper into the earth, the temperature of the earth gets hotter. That's what this line is, and this is called the geotherm. It's like geothermometer, and so geotherm just means as you go deeper in the earth, temperature goes up. And so diamonds can occur at the place where the geotherm brings carbon into the diamond stability field. And this depth is in the Earth's mantle. So we're going to say upper mantle. The depths here are like 100 kilometers to 160 kilometers, of course, or deeper. Even diamonds up to 500 kilometers down have been found. Now, getting up to the surface is unusual. And so here's like our layers of the earth, and if here's our continent, diamonds are forming down here. How do they get up to the surface? Well, we end up having a magma carry them. And so if a magma melts down here and starts to, by buoyancy, rise up to the Earth's surface, it can rip diamonds off the wall of the mantle and then explode them out at the Earth's surface. And this kind of a magma is called a kimberlite, and they're fairly rare, but there's enough of them that there's diamond deposits on all the continents. So we're going to say kimberlite magma brings up from mantle.